Okay, welcome back everyone, and thanks again to the Boeing Company for sponsoring this morning's coffee break. As a reminder, the questions could be sent to plenary_2@ICAO.int, so please send them after you have them formulated. We'd like to have a real good, robust discussion at the end of this session that we have here. I'd like to introduce the speakers for the second session that we have. First, we have Mr. Andrew Haitley of Eurocontrol, the technical coordinator of the Korus project. Next would be Mr. Frank Mattis, the director of Digital Aviation Market Development Americas for Thales. Third, we have Ms. Marta Sanchez, the senior research and development engineer at CRETA in Spain. And last, we have Dr. Abdul Ali, Achachi, the principal air traffic controller at the University of Batna in Algeria. Without further ado, we'll start off with Andrew.
Thank you. You're very kind applauding before I begin. You might not enjoy this. Just a quick introduction. What on earth am I talking about? So the Korus project was started a couple of years ago. It was an exploratory research project funded as part of the CESAR activity to write a concept of operations for USpace, which is what we call UTM in Europe. The Korus project was a consortium with 9 member organizations, some of which you may recognize: DFS, which is the air navigation service provider in Germany; DLR, which is a research organization in Germany; DSNA, which is an air navigation service provider in France; HEMAV, which is a Spanish drone operator, at one time measured as the 4th largest drone operator in the world; ENAV, the air navigation service provider in Italy; NATS, the air navigation service provider in Britain; Unifly, a company that write software for UTM, who sponsored yesterday's lunch; and the University Polytechnic of Catalunya, which is a university near Barcelona where you can do a master's in drones and things like that. They've been doing drone research for a decade or more. We also had a lot of people who were interested in joining the project when we set it up, and we organized a thing called an advisory board, which we ended up with 21 members. We also made contact with a large number of other organizations because the Korus project was seen as a transversal project for a whole load of UTM-related research that was going on simultaneously in Europe. And I was very pleased with Patricia's presentation earlier because the stuff that she described implementing was what we had described in our ConOps. I'll come to that in a little bit. We also set up an organization of interested stakeholders which grew to over 600 members during the life of the project, so-called USpace Community Network. So during the 2 years of the Korus project, we ran 3 large workshops. Our main visible method was stakeholder involvement. We would like to produce a work which is approved and accepted by a large number of people. So this activity was focused around these workshops. And during these 2 years, we developed a ConOps iteratively, and the final version is available for your download if you're interested. Okay, so what was the scope of what we were trying to do? We focused on the VLL, the area below, the volume below where the VFR traffic are, but we extended it into the control terminal area. We wanted to tackle the lower airspace. We were initially inspired to talk about small vehicles, small UAS, but in fact, the aim is to manage the space, so anything which is flying in there should be of interest to USpace. And USpace has been defined initially as a set of services. This might seem a rather odd way to describe UTM, but it was a method that was used in order to explain to a more general audience what on earth this might be. And we've drawn this little diagram which just gives a list of stakeholders and a rough kind of collection of their interactions with the system. And there are 5 principles driving USpace, safety being the first one, but we're also very much interested in social acceptance. The project included quite some work on social acceptance and acceptability indicators. We would like the U-Space to be deployable throughout the ECAC region. We would like it to enable an open market for UTM services, and we would like to have this equitable access to the airspace principle that was mentioned yesterday. And we also would like to produce a ConOps which we can walk away from and will withstand the test of time. So we immediately wrote our ConOps considering a high level of traffic. This is in some difference to other ConOps which are in use at the moment. A lot of a focus of our attention is on drone-drone interaction. We make very few assumptions about technology because it's a ConOps. It shouldn't imply particular implementation. And this is the kind of the interesting diagram that we produced in the 2 years, which shows how we retitle bits of the airspace in simple terms for a, let's say, less sophisticated audience. The drone users who are able to fly in Europe, some of them only need to read a leaflet, which is in the box with the drone. So we can't expect them to have a mastery of air navigation terminology. So we ended up with these three broad descriptions of the airspace. We described them as volumes, and they are X, Y, and Z. And the X can be considered where the low risk is, the Y is medium risk, and the Z is where the high density, high risk operations are. And Z falls into two flavors. There's controlled by ATC and not controlled by ATC. And the key difference between these three different volumes is that it's about where and how collision resolution is managed. And in the X, there is no service to resolve conflicts. So the conflict resolution is the responsibility of the pilot. So X is well adapted to visual line of sight operations. Anything else is a bit of a struggle. I mean, it is possible, but you have to take a great deal of care. Y is premised on the idea that there'll be some flight planning going on, and approval of the flight plan is an entry condition into Y. And this flight planning will enable what we call strategic conflict resolution, which is before takeoff, which is exactly what Patricia described. So the flight plans will be processed in order to resolve the conflicts. And the aim of this conflict resolution is to reduce the residual risk of conflict to an acceptable level. And this acceptable level is something which the regulator is going to have to work on. We stopped at that point in our work. And then Z, we have this strategic conflict resolution where strategic is before flight, and we also have tactical conflict resolution where that's in flight. That's not the same as detect and avoid, which we regard as a safety net on top of what's going on with the tactical conflict resolution. And then in the ZA type airspace, the air traffic control is in command, and the U-Space is there to provide services to enable air traffic control to do its job. So it's providing situational awareness to the controller, it's providing communication tools, and imposing standard ways of working. In the ZU, we have this idea that U-Space itself will provide the conflict resolution during flight from the ground. And I write that from the ground because this is, as I said, separate from a detect and avoid, which would be a third level of safety after the tactical conflict resolution. So this ZA is kind of why I'm here. We were talking about separation standards in the RFI, and unfortunately I'm not going to give you any distances or separation minima, but I'll just describe the kind of things which need to be taken into account. So the idea in ZA is the ATCO remains in charge. The purpose is to make the drone controllable in the same manner that he's used to controlling other traffic. And the U-Space should provide the necessary services to support that way of working. And the separation remains as the other aircraft. It's what the controller judges to be safe. So the only thing that might be new for him is the extremely low wake vortex category of the drone. The U-Space will provide planning tools which will allow the coordination of flights in the controlled volume. So there's a U-Space service called the Procedural Interface with ATC, which is how you would set up a flight that might have to cross an airport or that would take place in the apron area or something like that. And the U-Space will also provide surveillance information. We've assumed that surveillance for drones will be based on means which are not currently used by manned aviation. So there will be in U-Space some kind of tracking going on, and the result of this tracking can be passed into the ATC system and into the ATC world to be displayed on the controller's display as he would or she would prefer. And again, we see U-Space as providing communications channel. We don't expect the drone pilot to be trained for aeronautical phraseology. We do expect them to not really know what they're doing. So we thought it would be a lot safer if the communication would be through some kind of text messaging system using standard messages in the same style of CPDLC that the actors, the air traffic controller and the drone pilot would be choosing messages from a list and sending them to each other. This also has the advantage that the whatever equipment the drone pilot has can synthesize the message into speech to be relayed to his ear so he can continue to fly unimpeded while understanding what's going on. U-Space should also convert heights and headings to the appropriate systems because drones typically have true north and satellite navigation related altitude, as we heard this morning. The other thing that's going on is ZU, which is where we see as U-Space is providing the service which is going to stop the drones colliding with each other. And in the ZU space, the conflict resolution is by computer. There's no air traffic controller. This is done for a number of reasons, but it does raise the possibility that we can have different separation standards for each pair of aircraft. There's no reason to simplify it down to one figure because the computer can deal with the complexity of every pair of aircraft being separated by a different amount. And so what we talk about in our project are bubbles around the drone, and the idea would be that safe separation is that these bubbles don't touch. Now this idea has come up many times, different people have worked on this, and we in the Korus project had DLR as a member, and they have written a nice paper about this with some maths in it, so I would recommend that you have a look at the paper. And they produced this nice diagram, which I've stolen, which trying to give you an idea that this bubble will be sized dynamically. The size of the bubble will depend really on two factors: the CNS performance, how well we know where the thing is, or how well it can get out of the way if it needs to. And the second factor is the inherent risk. What is our willingness to allow these drones to come close together? And factors influencing CNS performance would include, among others, the weather, which would need to be incorporated into the modeling which is producing these dynamic bubbles. Risks related to the aircraft include whether or not you're carrying people, but also risks related to the location. If you're overflying a populated area, you would be less happy to have the aircraft close together. You might enlarge the size of the bubbles. We didn't go any further with this work. This is just a conceptual work. It's left for further research, hopefully in the next few years, to make this a bit more robust. But this was our idea. Now we have a little problem that we were unable to resolve in Korus, which was, is this ZU airspace going to be a controlled airspace, or is it going to be an uncontrolled airspace? So in the two columns, I've compared the two. In the controlled airspace idea, these messages which are coming from U-Space would be instructions, and the pilot would be obliged to follow them, or the piloting function if the drone was automatic. And so the U-Space service provider is thus providing a separation service in the classical ATC terminology. So ZU is a controlled airspace. And the question has come up more than once, what kind of controlled airspace? And we're kind of guessing, well, maybe it's Class B. But in fact, who knows? Because we don't know if visual line of sight and beyond visual line of sight are in the same flight rules, which are in the definition of Class B. Maybe there's some new kind of flight rule, in which case maybe some new kind of airspace class is needed. So hopefully that'll be dealt with tomorrow. But it's something which has troubled us. We can't answer Class B with any confidence because there's more work to be done on this. The implication of making this a controlled airspace is that the USSP needs to be built to a very, the UTM, U-Space Service Provider system, needs to be built to a very high standard. And the U-Space Service Provider needs to have insurance which is commensurate with the liability of providing a separation service in the classical sense. And there's also an implication on the communication needs. These messages providing this separation instructions need to arrive reliably. The contrast with this is to declare that ZU is an uncontrolled airspace, in which case these messages coming from U-Space are just advice, and the pilot remains liable and in control. The question then is how close do we dare put the flights if we don't really know if they're ever going to follow these instructions? So the resulting density of operation is likely to be pretty low in the uncontrolled version. And there may be a very strong reliance on detect and avoid if we haven't managed to achieve a level of confidence in this tactical separation. But again, we still have this strong reliance on communications, which we don't seem to be able to get away from. So this is the kind of core of my presentation today, but I just say that there is a little bit of a link with this bubbles model and strategic conflict resolution, which is the stuff Patricia talked about, which is done before takeoff. That again, the same kind of notion of the bubble can be used in the process of determining whether a conflict is taking place. We have, we're very fond of the idea that the flight plan information is just a probability of where the aircraft will be. And so the risk of conflict is determined when the probability of the presence of the two vehicles exceeds some threshold. And as Patricia said, the system will propose some kind of resolution for the conflict. But we imagine that the business needs of the drone operator will take precedence, and it's the drone operator who decides what to do to resolve conflict. And a question which maybe was triggered in your minds by Patricia's presentation, which was when should strategic conflict resolution take place? This is something that we thought about quite a lot. And one model which you hear mentioned quite a few times is first come reserves the airspace. And we were very unhappy with that in Korus. So we came up with the idea that the flight plans are going to arrive at any time. Some will be sent long in advance, some will be sent very short distant time in advance. Then that should not influence how the conflict resolution should take place. A conflict resolution should be much more concerned about optimizing the overall system. So the result that people want is the maximum capacity. They would like the most possible flights to take place in the available airspace. And one way to do this is to defer all of the conflict resolution until a certain time before takeoff. And we've called this required time to act, RTTA, and it was mentioned in our CONOPS. And it means that conflicts will be discovered but untreated until just a few minutes before flight, when finally some kind of overall solution can be found. And then if any flight plan arrives after that time, it has to just fit in with what's already been decided. So this is a model that we're proposing, a model that we believe is fair, and I'm interested in your feedback on that, not as I'm standing here, but if you want to discuss this with me or raise questions about it, I'm very interested to talk about it, because I think it's a problem that is not really being addressed very well in the work that's going on in the wider world at the moment. Okay. We've got some open issues. We're convinced that you can do this stuff from the ground if you have tracking, and we're convinced that strategic separation can be done based on planning to an extent, but we have some open issues. We really need surveillance to be working. We would like the communications to be working, and we would like somebody to do some work on this CPDLC-like service, and we would like somebody to have a bit of a think about this responsibility and liability issue. And we have to do some work to flesh out the details of the processes involved. We've just given a high-level overview in Korus, but there's still a lot to be done. And one of the questions which comes up is like, on what basis will flight plans be rejected? Is there some kind of legal footing that will allow this? Who's in control? So many questions need to be answered, and I invite you to try and answer them in the future. So thank you very much.
Very great. Thank you, Andrew. So next up is Frank, please.
Thank you, Randy, and thank you for having me here at Drone Enable 3 this year. So I'm Frank Mattis. I'm the Director of Digital Aviation at Thales, part of the Airspace Mobility Solutions Group, formerly known to you guys as the Air Traffic Management Group. But in seeing how our industry is changing, we're also changing as a company. So trying to integrate the which is a term I know we're not supposed to use as of yesterday, the new entrants into aviation, but also find new innovative solutions to address. This is not my slide deck, but I can brief those if somebody wants me to. Looking at the challenges that we face in integrating new entrants. So. Just as an uncomfortable interlude while my slides have come up. So a little bit about some of the work that we're doing at Thales. We are currently working on looking at low altitude airspace integration through UTM, but also looking at how do we integrate drones alongside manned aviators in a UTM ATM integration concept. So we have a number of projects that are ongoing worldwide to look at those challenges and how do we safely put manned and unmanned systems into the same airspace, looking at deconfliction models, modeling the overall airspace system, and also looking at a number of different sensor solutions, a number of different activities that we have in a multi-step process to validate how we get from airworthiness to pilot credentials to remote identification. And to also figure out a way to share information about flights between air traffic and UTM service providers. So,
Sorry, Frank, we're having some troubles finding your slides.
that's okay. They were underneath there for a second.
Did you see them already?
I did.
The ones that we have here is for another session. I think it's their session later on today. Nancy is this section. Yeah, so maybe we get JC. JC? Do I? We can do that. Just want to, you want to walk through it, or do you want to try to bring it back up another time?
The slides to do the presentation. So I'll be back later for round two. So over to you, Randy.
So Frank, our sincere apologies. We are looking for your slides at this point. So, all right. So we'll just move on to our next presenter. So, Marta, please.
Okay, hello. Hello, everybody. Thank you, Randy, for the introduction. Yeah, these are my slides. And well, it's not bad that we change the order because my presentation is maybe much more related to what Andrew just presented. So it's a way of having a continuation of the same discussion. So this presentation is about a vision on deconfliction and separation management in the framework of a more ample process of drone dynamic demand and capacity balance. The vision is based on a position paper which has been written by my company, which is CRIDA, an R&D center which is linked to the Spanish NSP, ENAIRE, and also in collaboration with ENAIRE and the Spanish General Directorate of Civil Aviation. So I will start with putting in context the discussion, talking about some specificities of the drone traffic management that affect the separation standard and the separation management. The first one is the scale effects. So one of the main difference between the ATM and the UTM is related to scale aspects. So we had different scales from the traditional ATM system in weather, in geospatial information, in the operational timeframes, and those scales affect the way we need to separate the drones between them. So if we want to do separation in an effective manner, we need to take into account and to adapt to that scales. For instance, taking into account the micro weather, or for instance, adapting the vertical separation to the geospatial status. The other specificity is very obvious, which is the diversity of drone performances that we can find. So this diverse environment of vehicles and their performances also implies diversity in the needs for separation. So we need to have different approaches. For instance, the time-based separation, and not directly having the same separation for all vehicles. This is related to what just was commenting about the pairwise separations. And also we may require UTM navigation performance for certain airspaces. The diversity of performances in drones is also linked to another specificity, which is the diversity of missions. So in the DTM, we have different drone operators with very diverse possible mission targets or operation targets. And that means that the flight planning management is linked to the mission management. And certain trajectories implies uncertainty in the execution, because otherwise you cannot comply with the mission objectives. And that should be also taken into account when defining a separation management procedure. We also have drone swarms, and that means that we can have a group of drones flying together, or we can even have drones that are flying, flight plans that are interlinked between them. And we have maybe to separate those drone swarms in a consistent manner. I mean, the swarm being separated, integrated from the rest of the traffic. And the last specificity is the dynamic nature of the separation. And this is linked to the CNS system, especially the navigation and surveillance system, which is the enabler for the performance of separation management in DTM. And this system is dynamic in nature. The performance are not stable. And that also means that we will have to adapt to this dynamicity when defining a separation procedure for the drones. The CNS technologies, the CNS architecture or infrastructure in place has an impact on the separation standard, as I say. And the performance is dynamic, but is also different depending on the environment. And here I would like to introduce a European project, which is the Terra project, funded by the European Commission and the CESAR joint undertaking, which is currently ongoing and is looking at possible CNS architectures that will meet the requirements at the different environments to enable the drone operations. In this slide, we can see the part of the work being performed or that has been performed in this project. And the project has evaluated 3 different environments and 3 different use cases linked to those environments. We have evaluated the rural environment and an agriculture crop business case, suburban environment with infrastructure inspection, and the urban delivery in the urban environment. And in those environments, we have defined requirements that has to be met for each part of the CNS system, for the communication, the navigation, and the surveillance technologies to enable the operations and the use case that we have analyzed in particular. And in this slide, you can see just an example. I don't pretend that you read all the information that's in the slide, but you can see an example for the air-ground communication technologies. And in red, is the urban delivery use case in the urban environment. And in red, you can see the line which is depicting the performance requirements in the parameters that we have considered, such as availability, integrity, even the coverage and deployment, to enable the operations that we have studied, in this case, the urban delivery. And you can see a number of lines of the technologies that we have analyzed. We have analyzed current and future technologies that are not yet widely available, but that will be in some time. And we have confronted the performance that are provided by those technologies with the requirements in each environment and for each use case. And with that, we have proposed, or the Project Terra has proposed, a different CNS architecture which will enable the operation in each of the environments. And this is the starting point to define the separation procedures, but because the performances of the CNS architecture in each environment will be, as I say, the enabler for the separation management procedure. Here, I will like to make a small digression and to highlight one of the remaining challenges that is linked to separation management in VLL, in the very low level airspace where UTM is expected to take place, and is related to the manned aviation integration into the VLL. It's a challenge because nowadays not all space users make themselves visible, and there is still ongoing work in the operability between the UTM and the ATM system. Ways of addressing those challenges will be related to the definition of low-level flight rules for the VLL airspace, where demand traffic will be integrated and comply with those rules and be managed also by the UTM system. Required for that, for instance, we will need to have electronic conspicuity of all vehicles and situational awareness, for instance, with the use of UTM services such as traffic information. And also other possible enablers will be related to the submission of an operational declaration or a flight plan for every flight that will be entering the VLL airspace. Okay, so with this context, we can already talk about as I mentioned at the beginning of the presentation, the possible life cycle for drone demand and capacity balances that will be linking the strategic deconfliction and the tactical separation management during the execution phase. So in this slide, you can see a proposal for this process, which start with the drone operators that will be defining their mission plans and the associated flight plans, taking into account certain environment constraints, such as the weather. And again, here we have to highlight the scale of the weather that is being used to derive the flight plan that are needed for certain missions. And we have to take into account also the performances of the drones that are available for the missions and how they can meet the defined flight plans. So once we have certain demand clear, the other side of the picture will be related to the capacity characterization. And here is another specific characteristic of the DTM with regard to ATM. Again, we have the weather, as in ATM, but in a different scale, as I said at the beginning. But then we have to take into account other approaches for the capacity. And here put risk-based capacity, because in DTM, we cannot rely on simple counts or on the density for a given airspace. We will have to take into account the risk of mid-air collision, for instance, taking into account certain constraints or characteristics of the airspace. And here again, the CNS system, the infrastructure in place, and the performances, the current status that is expected for the execution phase is important. There are other factors, such as the population density, what was mentioned also also this morning, and that affect the severity of the occurrences, not just the risk itself, but the severity. And there are also other aspects that must be taken into account for the capacity of the system related to the societal impact. I put here the sample of noise. With that and other framework characteristics, we will have a view of the available capacity in the airspace, and the other characteristics will be related, for instance, to the airspace structure in place or to the low-level flight routes, as I mentioned before. So with that, the strategic deconfliction can be performed as a UTM service, and we had an example previously, which will be invoked by the flight planning management service in cases that the demand exceeds the capacity. And that service can confront flight plans between them, and also the flight plans with the available capacity in their space and other constraints, as I mentioned. And once the strategic deconfliction has been performed, we can move to the tactical separation management, which will still be needed, even if the confliction has been performed. And that is the matter of the next slide, so we move to that one. And here we can talk of certain enablers for having a tactical separation management in place. The first one is the situational awareness, and here I propose to use certain UTM services that are critical for that situational awareness, such as tracking or traffic monitoring and information. The second enabler will be related to the low-level flight rules. We will need rules of the air and also priority, but priority can go further to the simple priority link to different missions, and that was introduced before as well by Andrew. There are other considerations, such as the global capacity of the system or the efficiency. So, for instance, I put the question here: should faster drones have right of way to improve the capacity or the efficiency of the whole system? Another thing is the use of vehicle-to-vehicle technologies. Currently, they are not mature enough to be used as a primary separation management tool, but can be used as a safety net, so it's an enabler also of the separation management that we put in place. And last but not least is the concept of dynamic separation minima. So it's related to the bubbles, again, that we saw. Can be performed with bubbles, with weights to the vehicles. And the important thing is not the way exactly we perform it, but that the separation between two vehicles must be dynamic, but must be pairwise, and must take into account, as I say, the status of the CNS system and also other factors such as weather or the drone performance itself. So that is related to the strategic deconfliction and separation, and I will go to provide a hint of the modeling and simulation that is being performed related to the study of possible separation standard or separation minima definition. So there are fast-time simulations used to test how the system will behave with certain level of traffic in certain environments, and with certain defined separation minima and rules of the air. For those fast-time simulations, we can input the CNS architecture that I explained before with nominal performance. The traffic mix based on the certain traffic prognosis, certain mix of traffic linked to the operations that are expected in a certain area, linked to the business cases that will be taking place in a certain environment. And also aspect related to the environment, the flight rules in place, and the non-nominal situations that we will need to consider. Because in the fast-time simulation that are being performed, for instance, in Terra project, as I mentioned before, and in CRIDA internally, we are performing also some tests. We want to test degraded conditions of the CNS system and also non-nominal situation to be sure that we are in the safe place for the establishment of a certain separation minima. And the results will be related to what we are measuring in this fast-time simulation are related to mainly safety as performance, as key performance area. There will always be a residual risk of conflict. We are not aiming at having no risk at all, but that will have to be maintained to keep at a minimum to allow operations. And once we reach that certain level of safety, then we can focus on other key performance areas such as capacity or time efficiency, which are also dependent on the separation minima and the separation procedures that we define. So that's all for the presentation. I hope you enjoy, you find it interesting, and I wait for your question in the last phase of the session. Thank you.
Thank you, Marta. And Frank, we have found your presentation, but we'll save you for last, though. We'll build the anticipation up more. So next, Dr. Atrachi, please. Give them a second while they take care of this piece, and they'll bring your slides up shortly. Yeah, forward, yes. Yeah. So we're doing pretty good on time, so don't feel rushed or anything. Okay. This is probably a good time to do a service announcement. Bring your emails. Please email, so we'll have time in the end to go do the questions. plenary_2@icao.int.
Ladies and gentlemen, good morning. I'd like to thank ICAO for inviting me to present my paper entitled Deconfliction and Separation Management for Drones in UTM ATM Airspace. The plan is the following: introduction, separation between manned and unmanned aircraft, communication, navigation, and surveillance equipment, supporting deconfliction at strategic level, supporting tactical separation management, and conducted modeling and simulations. And conclusion for some recommendation. Everyone knows that the demand for airspace access is growing fast for UAS. What solution have to be performed by ICAO, by states and industries? We separate we have three kind of airspace. We have ATM airspace, which is a huge airspace when all manned aircraft are flying. In this airspace, unmanned aircraft can fly, and air traffic controller have to ensure standard existed separation between manned and unmanned aircraft without changing. We have the common airspace, which is airspace where unmanned and manned aircraft are flying. For example, an airport inside a town. We have the activity of manned aircraft, and we have also the activity of unmanned aircraft. For UTM airspace, we have established a table of some separations depending on the type of UAS, moving wings UAS or fixed wings UAS, and depending on traffic density also. For this task, we have some tasks to ensure: detection, tracking, identification, and avoidance. We have to use some equipments, VHF and UHF frequencies, GNSS signals, and ADS-B signals, TCAS and transponders, avoidance obstacles systems. These systems must be used to facilitate the integration of UAS. The GNSS signals have to be used to give the right or the accurate position of each UAS. And in order to overtake the problem of communication, we suggest to use solar UAS at high altitude as a link, as a relay between different ground station and different UAS in some area. In order to identify the capabilities of operating UASs, including flight plan data, weather, surveillance, scheduling, and separation services, we have to use the artificial intelligence, which consists of teaching UASS system. We have to teach UASS system in order to give solutions or to react in critical situations, because we cannot program all the scenarios in the UAS. We have to use artificial intelligence in order to get the best solutions in case of failure communications or in critical situations. This is a collision avoidance system logic. It's an organigram which is based on position test and altitude test between two UAS, and we can use more than two. We can use several UASs and maybe obstacles. In order to test the proposed model, we use simulations, and these are some results. Simulations between different UASs to test and to check if the UASs react in the best way. This is the scenario of two UASs face to face, and we can see that each one can avoid the other by turning right, as mentioned in Annex 2, the rules of the air. So each aircraft or each UAS have to turn right to avoid the other one. The certification testing and operational evaluation, they must be done with conforming prototypes, procedural, technology innovation, a method of measuring and verifying, and efficiency and reliability. As conclusion, we have some recommendation to say. Everyone have to work. Everybody have to work together in order to implement and to enhance procedure and reducing. We use the reducing separation between UAS in low altitude. The integration of UTM ATM using boundaries. The boundaries must be defined to protect manned aircraft and protect passengers. We have to use simulations and mathematical modeling in order to test and check the new separation if it is good or not, and we can change it if the result of simulation are not good. We can change, and we can use other data, and we repeat the simulation many times in order to get the best results. We recommend also to certify all UAS, and we recommend that pilots, UAS pilots, have to follow certified training in order to be aware of the integration of UTM and ATM systems. Thank you for your attention.
Okay, great. So we're down to Frank now. We're going to try him again. We do have your presentation.
Thanks. Yeah, that works. Hi, remember me? I was up here before. We'll try this again. I'll skip the introduction. Thank you again. And so just kind of building on the discussion that we've been having all morning about deconfliction services and how we continue to modernize the air traffic infrastructure to accommodate UAS and manned aircraft in the same space. We really look at airspace integration as a major challenge that we're facing moving forward. So Low altitude airspace usage is forecast to be orders of magnitude higher than existing commercial aviation demand on the existing air traffic system today. So if you believe the numbers that we're seeing in forecasts, package delivery alone will be almost 100,000 times greater than what we're seeing from manned aviation demand in the commercial sector. Integration of UAS into air traffic management must always accommodate and must always have safety first as the number one tenet, and a reliable infrastructure to support operations in the area of communications, navigation, and surveillance. So it's a term that we've been using as an industry for over 3-4 decades about having a reliable infrastructure in place to accommodate the growth. At no point in our aviation evolution is that more important. So we're getting away from traditional ATM infrastructure that has protected frequency bands, accommodates aircraft and helicopters and general aviation that behave in a certain manner. But now we're going to have to find a different way to leverage commercial infrastructure and also potential existing infrastructure to accommodate changes to the airspace system. Efficiency will be something that we need to also take a very close look at. Minimum flight energy for unmanned systems that likely have a very limited battery usage time to complete a mission. In-time arrival, balancing demand versus capacity of the overall air traffic system and when and where these platforms can operate. And then finally, looking at cost and efficiency. So if we do slow down the system, there's an impact to the UAS operator for completing that mission, but there's also an impact to and the efficiency of that mission, but also looking at the efficiency of the overall system. So if we do slow things down and accommodate safety and capacity, what does that do to the overall efficiency? So we'll talk about that in a little bit more detail in a couple of slides. So how are we going to accomplish this? So I think, before we go out and start doing wide-scale trials and integration, we really need to model the airspace. We have to have a configurable flight environment. We need specific traffic patterns and mission styles to be modeled as part of the overall system. And we need to gather data to improve the demand and capacity flow and equity of traffic distribution within our local communities. So in air traffic today, we have most of our policy being set at a national level. I think as we continue to evolve the industry, we're going to see more involvement from local communities as to how they want their airspace management or their airspace structure managed and control of localized operations. But above all, I think we need to look at the implementation of a trust framework for airspace access. So the guy that did the introduction before alluded to a 10-step process of looking at everything from airworthiness to pilot credentials to cybersecurity protection to a reliable CNS infrastructure, and then services that are provided back to the drone operator at the end to improve drone missions, where missions are flown, the types of missions that are flown, risk-based profiles for those operations. So all this has to come together in a very orchestrated manner for the overall system to function. So what Thales has done in an area in central New York, you may be familiar with the UAS corridor that is being deployed in central New York State between Rome, New York, and Syracuse, New York. We've taken a look at modeling some high volume, medium volume, and low volume operations in and around the city of Syracuse. Just kind of arbitrarily looking at the airspace system to see, as we do increase the number of UAS operations across an urban area or suburban areas, what does that do to the overall airspace picture? So, as you'll see here in the diagram, we have specific takeoff and landing spots across the city. We looked at multiple routes that balance the traffic load based on access that certain credentialed pilots and platforms could have. But then we also looked at just the amount of sheer volume based on time that would have on the overall airspace system at a very localized level. So as we look at airspace deconfliction, there's really kind of two areas that are emerging, and some call it strategic deconfliction versus tactical deconfliction. We look at it as reactive versus proactive in a modeling and simulation environment. So in a reactive environment, the USS is really kind of at the center of everything that's going on. in the planning of the low altitude airspace system. So one of the large tenants that we have at Thales is also looking at an airspace arbiter who will look at mission plans, be able to arbitrate the airspace system, ensure that we have a good balance between manned and unmanned systems, and equitable access to the airspace. So it's not just a first come, reserve your airspace volume and go fly. But there are elements of the USS model that we think can certainly work to the industry's advantage, and we need to take a look at those. So one of these discussion topics is, letting the UAS and the USSs decide how to deconflict themselves. So each UAV would sense its environment, detect a potential conflict, and adjust its overall trajectory for its particular operation. So that's one model that we're looking at as this concept continues to roll out. Then there's a proactive model, which is oftentimes referred to as strategic deconfliction. For every UAS entering the flight zone, trajectories are carefully planned so that there won't be any conflicts between the UAS or potentially other manned operators that are in that airspace system. So it does slow down the system, but it also eliminates the potential for conflict between UASs in that particular set of airspace. So the airspace manager will foresee that potential conflict based on flight planning, weather conditions, time of operation, and adjust the overall trajectory of that operation before it takes place. So when you compare these two, and you're looking at computing power or human in the loop that needs to be a part of this, reactive and proactive have significant trade-offs. So demands for computational resources, communications resources to maintain constant command and communications link with that particular drone. Resulting traffic patterns are highly complex and sometimes unpredictable, as we have a free flight condition that is emerging. Reliability of predicting those potential collisions becomes a lot lower because of the unpredictability of the overall operator within the system. And flexibility may be high within the system for specific flight routes, but it also would create conflicts that may not otherwise easily resolvable. On the proactive side, when we're looking at trying to orchestrate how drones enter the airspace system, demands for computational resources, potentially cloud hosting, are quite a bit lower. Resources for maintaining communications with that platform are more predictable and therefore lower. You don't have to have the constant update rate, constant bandwidth usage that you would need for a free flight situation. Traffic patterns are regular and predictable. Reliability of the overall system and the acceptance by local communities and UAS operators would be high in this situation. And flexibility, even though a little bit lower, would increase the overall level of safety in the system. So if we were to take a vote, we would vote for this proactive part. That's why we circled it. So as we looked at using the City of Syracuse model from a couple of slides ago, this is really what you see, and it's kind of an eye chart. And if you look at it very closely, the yellow points indicate conflicts within the overall airspace system. So between the start areas and the end areas where the drone actually has to fly, there will be a number of points of conflict as those operations continue to take place. This is simulated over the course of a one-day period. We arbitrarily pick some numbers that look like high-volume operations. We will have some package delivery services that are coming to the local area that may take advantage of the overall airspace. So we showed that as a high scenario, and a low scenario being public safety sort of applications, the one-off drone user here or there that may enter the overall airspace system and may have to fly from point A to point B. So you'll notice that as you continue to look through this particular scenario, the number of conflicts will actually increase as the traffic load increases. There's no surprise there, right? So in a free flight environment, you're going to see a lot more conflicts between the drones that need to be resolved on a much more tactical basis, and that'll be done at the UAV level, but also through a highly computational service through the UTM and ATM integration platforms. the conflict ratio also would increase as traffic increases. So a number of separation violations, separation not being the appropriate term for drones at this point in time, but kind of gives you a sense of what we're looking at there. Once we implement routing and a predictability within the system, you're going to see that the number of conflicts goes down to almost zero. Will it ever be zero? Probably not, but pretty close to zero is what we can hope for. So adding predictability, looking at trajectory-based operations based on time, capabilities of the operators that are participating in the overall system. Flight time would be reduced, and the number of operations would also be reduced to accommodate a safer airspace situation to emerge. But overall, you still have a high number of operations that take place within the airspace system. But the best part, the resulting effect is really no conflict between the UASs in particular. So as we're looking at the route structure and not just putting in place highways in the sky, if you will, the deconfliction capabilities are a certain part of it, but it actually, routing kind of exposes other things that we have to think about as part of the system. So as we looked at particular operations and where they flew, we could see that, at certain points in the time during flight, they may be entering or exiting areas where you have overlapping communications coverage, surveillance coverage, areas that you may not want to fly over, critical infrastructure, schools, areas of community where you may have people that don't want flight paths over top of their house. Looking at cellular coverage, we can, in particular, if we're using the cell phone network as a means for command and communication, and even navigation, and sometimes surveillance, we can create areas where we have areas with good coverage and particular no-fly zones if we want to ensure that we have constant communications with those platforms. Those areas could maybe have certain outages at certain points in time, or there's an opportunity to fill in those areas with mobile systems if that becomes a necessity. So overall, the trajectories would avoid both permanent and no-fly zones. Would be able to introduce flight restrictions within that area, but also model it based on the overall reliable coverage that's underneath the system. So as we talked about before, we're also trying to balance the demands of the UAS operator. So the UAS operator has a business case to meet. They're going to be more empowered in the system. As Andrew pointed out, we don't want them to be speaking the same language as air traffic control, the same jargon, the same phraseology. We really want them to be able to have their operations be enabled, but also find a way to do that in a more automated fashion. Introduction of artificial intelligence, et cetera, but more computational power within the UTM platform. Mission time also would be an impact where if we have a very specific route structure, chances are based on weather conditions or the flight route, mission time will be impacted. And because of that, battery life of the particular drone may be impacted as well. So that may negatively impact the business case by the UAS operator. We're also taking into consideration, as I talked about, local conditions, ordinances, people maybe not wanting drones to fly over their particular properties, or communities having a ban or pushing the regulations down to that level to figure out when and where drone operations can happen. We want to empower local communities to make those decisions. And weather conditions, which, as we've all experienced here in Montreal this week, and certainly is something that we are aware of in central New York, that also impacts how the routing structure would emerge. So if we're looking at areas where we have these good coverages and no-fly zones, we're starting to look at how do we piece together different service volumes to enable drone operations to take place in a corridor-type structure. So two ways to look at this diagram. So you have a top-down approach where operators are limited to where services may become available. But if you're a drone operator and you want access to the system, you're looking at this bottoms-up approach where trajectories or area-based operations and volumes can be added through these overall service volumes and allow you to fly from point A to point B based on your credentials as a drone pilot. So the overall service volume is created as to an area where we believe that UTM services would be available, and that could be a large geographic location. And then as you start to get down into the different layers, you really want to look at how to not only protect the drone and its operation, but all of the other situations that are happening simultaneously in the airspace system. So we're envisioning this not as separated airspace or uncontrolled airspace or segregated airspace. It's really how do we enable drone operations to happen in the context of the broader air traffic infrastructure that's already in place. So having an intended area for the UAS operation and then building on top of that, having a conformance area to ensure that you have a margin of error based on any number of conditions. Maybe the drone is maybe not reacting the way that the operator had intended it to. Maybe there's a safety conformance volume that's placed around the drone to allow for public acceptance of operations. We're looking at a conformance zone that would allow the drone operator to first have their geographic volume, which may be 1.5 miles or 2 miles of operation, and then surround that with a conformance volume. And then the overall operations volume, which would be conformance for safety contingency. So knowing that there's a drone operator flying their mission with a safety volume around it, and then surrounded by an operational volume in the event that some off-nominal condition is inserted into the overall airspace picture. Helicopter flight at low altitude, a pop-up VFR that air traffic has to now accommodate. It needs to have some level of flexibility within the system to react. So by putting this operations value inside of the verified service volumes, as we talked about on the previous slide, could be a way to do that. So these are activities and a framework that we're trying to explore in New York and connect them as part of the corridor. So we'll be expanding on this concept over the next several years. So just to wrap it up, low altitude integration, hard. We need to study the traffic and airspace metrics that best characterize the low altitude airspace, the capacity of the overall system, not only from how many drones can be integrated into the overall airspace, but from a CNS perspective as well. How do we accommodate the growth of traffic? How do we ensure that there's safe or consistent connectivity with a network to track and maintain control of the overall systems? Traffic complexity and congestion. Those will all be impacts on the overall system that we'll need to continue to model and take a look at. We need to compare strategic deconfliction and routing strategies. What's the right balance between the two, and how do we ensure that there is an infrastructure in place to ensure that we do not compromise the overall safety of the airspace system. Comparing the efficiency, as we talked about, low altitude airspace optimization algorithms will need to continually be refined. I think a number of us in this room have ideas around how we're trying to accommodate growth at low altitude, and then development of decision support tools, which accommodate both low altitude and the existing airspace system. So, what if scenarios, and trying to figure out the best way to optimize the system. So. So with that, I thank you and appreciate the time. Again.
All right, thank you, Frank. This time I'd like to invite the speakers from the earlier session to come on up and join us for the QA session. Hey, come on down. Yeah. All right, one, thank you for submitting your questions. I think my begging worked and paid off, so we have enough to, I think, fulfill our time for the rest of the session. So great. So anyway, the first one go to Dachi. In your presentation, you proposed that both the barometric and GNS altitude should be used and selected depending on the purpose. Does the altitude correction method accommodate for both mean sea level operations and also high level operations or mountainous area operations?
Yeah, thank you for your question. Actually, just in this, I propose the one potential option. There are no answer at that time. Of course, for the high level operation, it is best. It may be best option to use some kind of mean sea level, the flight level setting. But I want to say is what is the best option to be acceptable for all the participants for the airspace. So the one important thing is drone use the common altitude reference system for sharing the altitude information between manned aircraft.
Great, thank you. All right, see for Patricia. Is deconfliction always the first, always first come, first served?
Not always. We also have the possibility of define priority. So some authorized user, like can be the police or military or even emergency bodies, has the possibility to set the flight plan, the mission as priority, and then this mission has priority over the previous approved missions.
Thank you. Doug, how does decentralized CCAS fit into an architecture with the multiple USSs?
Well, with multiple USSs, what we're looking at is each aircraft would have the algorithm in it. So basically, the communication between each one of those is across the radio. So it's a radio communication. Requires very little bandwidth. Requires very little resources on that. In fact, it could be integrated into the onboard resources. Is that answering the question?
Doug, if you think it answers the question, then it answers the question. So I'm not going to judge how you respond with that piece. Great. So Marta, it is not clear what the role is envisioned for ATC or whether indeed human in the loop is planned. What are the plans for conflict avoidance? Can you speak to that?
So the ATC will have a role. Well, I'm not sure if my presentation enters in that question, but I guess the ATC will have a role in the opposite situation that I presented. I mean, when the certain drones are turned into controlled airspace. But in VLL, which is the aim of the drone dynamic DCB that I presented, we don't really expect that there is that kind of interaction unless there are certain manned flight that has to enter in the airspace and some coordination take place. But yeah, I think that resolves. Yeah.
Excellent. Thank you. Let's see, Dr. Chachi. The question is, what is the source of the table of separation numbers in your presentation? Was this a suggestion or was it a reference from a standard?
Thank you for this question. The table is a suggestion, contains many separation. We have suggested and we have tested using modeling and simulations. And it's up to experts to verify and to analyze these separation in order to adopt them later. Thank you.
Thank you. One for Frank. So, considering the number of drones predicted to be operating, do you think the route system you're proposing would be able to meet the volume of requests?
Potentially. I think one of the things that we have to look at is not everybody's going to be at the same altitude and low altitude airspace. You're going to have potentially different layers, and that could be based on capabilities. You can have directions like we do today in manned aviation, where east-west, north-south go at different altitudes. So I think, I'm a little skeptical to believe that we're going to have the amount of growth that we're actually talking about in the near term. I think eventually we'll get there. So I think there'll be time for us to think through how that route management structure in the sky actually works. So I think some of the things that we've learned throughout these last several decades or and over a century of traditional manned aviation, I think we can take a lot of those lessons learned and apply it to low altitude in the short term, and then continue to through advances in automation, machine learning, AI, as those technologies become more mature and more applicable for air traffic. I think we can then see how the system itself will evolve over time.
Great, thanks, Frank. This is one for anyone who cares to answer for this one. If not, I'll start picking and choosing. So how does your presentation or your analysis that was conducted, how did it accommodate or address latency?
Our situation, the latency is actually very, very low, within milliseconds, because you are basically over the radio type of communication. So there is no latency. It is basically real time. You can control the aircraft real time and communicate with the other aircraft. Say, hey, we're coming together. You'd have an automatic reaction that is pre-programmed.
Yes, Marta.
Yes. Well, it's a general question, but as I presented, there is a project called Terra, which have looking at the latency among other parameters for the CNS technologies and for certain current and future technologies for each part of the subsystem. So if someone is interested in knowing exactly the analysis, the requirements that we issued for each environment, or the results of analysis of the performance that the specific technologies can provide, I invite you to go to the webpage of the Terra project. You can find Terra project in the Cesar Joint Undertaking webpage and a link to the webpage of the project, and there you can download public reports that we have issued. So just to comment on that.
Great. Anybody else care to jump on that? All right.
Why not? It's me again. Hi. So latency in our simulator is also configurable. I think in that chart we showed how we can configure the communications in particular, and that's really what we're trying to model there to get as close to what we believe near real time is actually. So we're continuing to evolve that model. Near real time is the objective, but I think there's things that you have to take into account as part of the network as well. Latency of the network, the time it takes from the drone to transmit to that network. All things, again, that we're learning through traditional aviation that now need to be scaled and applied at low altitude and for a different class of users.
Okay, great, thank you. For Andrew, what is the RTTA time? Is it right before takeoff, 5 to 10 minutes, or undetermined?
So we had a figure of 5 minutes initially, and this was proposed at the workshop I showed the picture of, which took place in Rome. And we were roundly criticized for proposing 5 minutes. It was completely ridiculous. But subsequently, it looks like 5 minutes is actually a reasonable time because the same trade-off occurs in manned aviation in Europe when we do demand capacity balancing. The more notice you have, the more easily you can react. But the later the information comes, the more dynamic the system can be and the more efficient. And the figure in DCB in Europe of 2 hours was chosen with a conversation with the users, that the aircraft operators agreed that was a reasonable number. The same for our world, this required time to act, I would also hope that would eventually be drawn from a discussion with drone operators, that they would themselves conclude what's a reasonable balance between the disruption and the benefit.
Excellent, thank you. And I haven't forgot about you, Aaron. So you're the only one that hasn't had one yet. So, and I believe this one came in your presentation. Was there an optimum lateral distance identified in your analysis? And if so, what was the target level of safety identified with it?
So there wasn't a single one because it will depend on the other parameters that you put inside the model. So it still depends on your max UAV velocities and uncertainties, etc. So the analysis we showed there, one of the numbers, if we were looking for a target level safety of 1 times 10 to the minus 6, was about 76 meters, given the other parameters. So it's hard to say there's one number because it depends on what assumptions you want to make about how fast things are flying on those tracks, etc. So it's hard to give you a single number.
Okay, all right, great, thank you. Let's see, again, what do we have here? Frank, so in your slide you discussed the notion of free routing versus proactive routing. You touched on the notion that proactive routing may result in a longer route and higher cost to the operator. If you're an operator, why would you want to accept that?
I think you'd want to accept it because you're part of a larger system in general. So you may have a longer route. It may not be as efficient, but to first gain the credentials to fly in the system, I think is first and foremost what we need to build towards, the trust framework to allow that mission to take place. I think you have to also look at other conditions that may arise there. Services that you would get from a UTM provider, things like conformance monitoring for your route, which could be a trade-off that you might not get from a free flight sort of notion. You can get more reliable communications linked to your platform. Having additional safety built into the overall system, I think, is an appropriate trade-off, and it may impact your initial mission, but services that could be gained through the UTM service that you might not otherwise get could be that appropriate trade-off.
Sorry, thank you, Frank. Well, okay, so we made it to the end. This wraps up our morning session, and I'd certainly like to thank all the speakers, both providing a response to this year's RFI and also sharing the ideas with them today. If we could give them a round of applause, please. Okay, so this afternoon we're going to return to a single track, so the wall will disappear during our lunchtime for that. It reconvenes at 1:45, and the speakers are kindly requested to arrive at 1:40. And it's now time for lunch, and lunch is being sponsored by DJI today. So thank you for your attendance. Enjoy lunch.